Hello, everyone, and welcome to our next AIM webinar, Accelerometers in Racing Data Analysis. Always something that is something that's uh, been a question that we've gotten quite a bit. The accelerometers, is GPS based ones okay? Is it sensor based? Is it, what is the right one to use? How do I use some of these? How do I filter them maybe a little bit better? There's a lot of information on accelerometers that we get a lot of questions on, and so I thought this would be a good chance to take a look and see and chat about it a little bit. So welcome everyone for being here, and I think we're gonna have a good time. We've got some the presentation has for those of you that are watching live here tonight, the presentation is there available for you if you want to download that as a PDF and be able to chat at it, look at it later if you wish. For those of you that are watching later on YouTube, all of the links that we chat about here today and mention will be in the description below, where you can go ahead and grab those at any time in the future. So keep that in mind. Okay, so welcome. I'm Roger Caddell. I'm the National Training Manager for AIM Sports here in North America, and this is something that we've been doing these webinars since the pandemic hit in March of 2020. We've been enjoying ourselves quite a bit with them, and pass around a lot of information, and it's been a great time. I've learned a lot, and I hope others have as well. So if you have as we kind of start this off, as you're watching this live or later, we've got 2 or 3 more webinars planned, and then we've got a couple at the end of the year that we do not have topics for yet. I am open to taking in topics for the next few webinars, and certainly the ones right after the new year. So please share with me if you'll have contact information at the end of the webinar. The my email will be shown, and share those with me. We're open to going some different directions on some of the different stuff that we talk about. So share those with me if you can. I'd appreciate it. Let's talk about accelerometers. The the biggest question comes always is what we have GPS based ones, and we're going to talk a lot about those. And we also have sensor based ones, and there are a lot of external sensors that can be purchased and brought into your AIM data loggers and brought in if that's something you wish to do as well. So we're going to talk about that a lot. And from the screen that you can see right now, you'll see something that you're going to be able to watch pretty much as we go through all of the slides. That when I'm using, showing you some sample data, there'll be, you can see here there's just 2 lines on top of each other. The format that I've followed is the blue one is the GPS based trace, and the matching sensor based trace from the inside of the AIM dash loggers typically is in red. So that should be something that your eye should be able to get trained on and get a pretty good handle on it. We'll talk about it as we go as well, but that's we're going to talk about not necessarily explaining that one is better than the other, or this one you always want to use in this case, or this one's this case. We're going to talk about what's good about them, what's bad about them, when you have challenges in using certain ones, and when other ones work better. And it is not uniform across not only road racing, but other forms of motorsports as well. So we're going to talk a lot about that. And I've tried to find as many examples of different forms of motorsports as I can, and I hope that you will. We've talked about this a lot here, but sometimes people will blank out a little bit if they see a dirt oval kart, and they think that data is nowhere near anything they can learn from. But I want to show you these examples, and in the reality, the same thing that we do in a drag situation or a motorcycle or a off-road car is the same thing you would do in a dirt kart oval or a road racing spec Miata. So it's we use the same data, and we use it almost exactly the same way, and it's and hopefully you'll be able to see that and learn from that today as well. So let's jump in and start going through a few different things. Different accelerometer sources, following basically the same process we did last webinar with GPS-based speeds versus wheel-based speeds. We're going to talk about the different ones, the highlights and the challenges and the pluses and minuses, and then go into some examples. So there are different accelerometer sources that we typically have available to us with your AIM loggers, and one of them is a sensor that's built into your dash logger, or the your Micron, or your Solos, or your Evo 4s, Evo 5s. There, there was a period there when the sensors weren't in there, but all of the 1.2s and 3s now are back, and they're in there. So a lot of you, if you should be seeing those. So you've got the sensors in there. Not only is it an accelerometer, but it also has pitch, roll, and yaw. It's got the gyro information in it as well. And this diagram gives you an idea of a little bit of what that looks like. And we're going to look at data from all of these sources here in just a little bit. So the uh, the interesting thing is the GPS is giving us the standard GPS, just the standard GPS 09 or the 08s, or any GPS sensor from AIM, also is giving us GPS-based lateral and longitudinal acceleration. The arrows here are not necessarily in the hard coded. It's not always in direct line of the antenna cabling coming out of the antenna. It is the direction of the antenna. So you could have that antenna spun in any direction, and your lateral and longitudinal is going to be true with the axis of the car. So keep that in mind. This is drawn in a way that might trick you into thinking that the cable always has to be in line with the direction of travel, and that's just not true with the AIM GPS sensors. So it's all based on the location of the car, and timing and speed and and a lot of math. So keep that in mind. But the dash, though, however, does have accelerometers built into it, and they do need to be square to the world, or you would have to do some math in order to do some work with it. But the having it squared up in the car is important. And so you don't want to place it. I've had some guys that'll place it over here in the center of the car and rotate it like 30 degrees to the center line of the car so they can see it better. And the trouble is now all of a sudden we're having to do some, the cosine of the angle, and doing math in order to get some math channels in order to get the lateral and longitudinal to be correct again. So keep that in mind when you mount them all. The dash loggers need to be squared up. That's an important thing. The same thing with the pitch, roll, and yaw. They need to be squared up that way, or else they will not work as well either. So keep that in mind as we go. The strengths of the GPS-based lateral and longitudinal accelerometers is their strengths and weaknesses, just like the GPS speeds from the last one of these we did. We talked about strengths. The technology continues to improve. There is the GPS 09 is substantially better than the 08, and the 05 before that was there was a big gap from the 5 to the 8, right? So this technology just continues to improve. Normal electronics gets better, cheaper, takes less power, runs cooler, right? Every step of the way. So the price is now lower as well. It's virtually included in every AIM system that you get. There's a GPS sensor in the box, so there's really not any good reason at all not to use them, have them in there. And with the GPS lateral and longitudinal accelerometers, it's plug and play. There is no configuration, there is no calibration, there is no setting of sampling rates. It's literally just plug the thing in, and 99% of the time the CAN network is working. It will take a few minutes for the very first startup, which maybe is a little bit of a weakness, but the very first time you ever start it up, it doesn't know if it's still in Italy or if it's in California or Virginia, or it's wherever you're at in Kansas. That very first cold start takes a little bit of time, and we're only talking minutes, but it takes just a little bit, and all the warm starts after that or hot starts after that are instantaneous, right? So keep that in mind the very first time. Make sure you push it out of the shop and just turn it on and let it run for a while, and it will learn where it's at and grab all the files that come down from the GPS in order to make it work super fast and super accurate. The weaknesses, just like with the GPS speeds, the relatively a low power signal coming down from all those satellites, and you can just be under some leaves and not get a good signal, right? Again, more satellites now than ever before, and some of them are higher powered now, so that is much less of a problem than it's ever been in the past. But still, if you go under a bridge or if you go underneath a canopy of trees, you will lose some of the accuracy. Electronic electronic technology can have issues. I thought about pulling this one out, but I've left it in there. In the past, you could have another antenna right near it, or and near to your GPS antenna, and keying up the radio. Sometimes the noise would get into the cables and some other things. That is virtually gone now as well. But electronic technology still can have issues. Obviously, antenna must have a clear view of the sky. I've had some people that have mounted their magnetic backs on these GPS sensors, and I've had them just throw it uh, vertically on the tunnel in the car, inside the car. It's been a while. Everybody I think has learned this, but they just threw it on the side there and thought, okay, well, we're good, and down by the driver's feet, right? It's like, no, these things need a clear view of the sky. So make sure you do your best. Boy, I think I saw there was a chat in there a little bit ago that we make not only ones that are just magnetic, but some that have a post out the bottom that is a roof mount, that you can actually just drill a little bit of a hole there, and the antenna comes right down inside through the roof, and a nut, and that antenna is up on the middle of your roof, where you get the absolute best GPS reception that you can get. So if you don't have that, you can use the magnet to put it up on the roof. If you've got a plastic roof or some sort of a fiberglass roof, just a dab of silicone, stick it on there overnight with a piece of tape, and just let it sit overnight. They will stay then as well. So they're fairly lightweight, and it just needs a little bit of stick to keep them on there. And then the last thing we talked about a little bit before is these signals come in from these satellites that are way up in the sky, right, and out in outer space, and there is a couple of problems that can happen around buildings, around chain link fences, in urban areas especially is where we see this. I've seen it a little bit at Coda with the aluminum grandstands that are right alongside the track. But sometimes that signal will come out of the satellite. It'll come down and it'll bounce off of an object and then get to the car. And since this entire thing works on time of flight from the satellite to the GPS receiver, and it takes all of those 20 of them that it gets, and it puts all the math together, and it comes up with that trilateration, you end up with knowing exactly where you are on the face of the earth, and it's doing that 25 times per second, right? But if it bounces, that one there took a lot longer, and it all of a sudden that it'll move your car over by 4 or 5 feet all of a sudden, right? We call that non-line of sight, where it bounced and it didn't get the signal straight to it, or multipath, where the signal got in and it bounced in. And AIM has done a good number of tricks and things they can do to mathematically clean all that up before you ever see it, but that still can be a bit of a problem. So I know Matt was in Detroit, and you were running down through the city streets with huge buildings with glass and aluminum, nothing but that in a tunnel, and that one was a bit of a struggle. That was the first one we've had struggles with on GPS quality in a long time. So that was interesting. So that's some of the weaknesses, but some of the strengths are pretty darn powerful for the GPS-based accelerometers. Sensor-based, some of the strengths on those is they're internal on almost all data loggers nowadays. They're user definable. When you have a dash logger like what's pictured here, you can't. We're expecting that you are going to put that dash logger in front of the driver, and so the orientation is such that we don't lock you in 100%, but it's lateral is this way, longitudinal, and vertical is straight down. Some of the loggers, or the PDMs that we have that have accelerometers built in, where you can mount those things in any direction you want inside of the software, you can pick which face is up on the box, which what orientation do you have the box in the car, and then all the accelerometers are automated for you at that point. Once you just tell it how you bolted it into the car. The last thing I'd like to talk about is the mounting of accelerometers. Not the last thing. We're going to hit a few more things here, but when you have an Evo 4S or even a PDM or an Evo 5, if you bolt that thing solid to the chassis, there will be some harmonics and vibrations that are pushed on into the accelerometer if they're mounted solid. All of our dash loggers have rubberized mounts that take a lot of that out of that and clean up the signal right off the bat. But in some of the other loggers, we don't have that. So what a lot of people do is they'll use that 3M hook Velcro, that really high end Velcro, and they'll stick it down with that. Maybe they'll put a couple of bolts loose in it just to make sure it doesn't fly off. But I've never had one fly off. But putting it on a Velcro base, some sort of a rubber base between there to get to take some of those harmonics out of anything that's accelerometer holds an accelerometer will give you much cleaner data. That high frequency movement of the car, especially karts and things that have no suspension, and the motors aren't motors on karts are a single cylinder. There's no balance shafts, and there's a whole lot of vibration from the motor, let alone the chassis and the rest of the kart. So keep that in mind as you're mounting stuff. You'll be a lot better off if you mount that in that way. Not only do we get the accelerometers that we're talking about, but of course we talked about it a minute ago with the image shows the gyro where you get pitch, roll, and yaw. And on many of them nowadays, we also have a magnetometer in there. And what that is a lot of people aren't using it yet, and it will be able to be enhanced in some software stuff that's probably coming, and users can write math channels around it. But when used with the accelerometers and the gyros, it can really enhance the headings and the and altitude numbers that are coming out of the logger. So that is in there as part of that those IMUs that are built into those. Weaknesses: there's a little bit more work. You must calibrate, and and probably orient them. As I mentioned, the dash loggers are pretty much, we figure out, and by default they're set up. But the Evo 4s and the PDMs, you need to go in there and you need to tell it how that box is mounted, so we understand, so the software understands which direction the forces are coming from. You can mount them upside down. You can mount them any way you want. All those options are in there for you. The track slope and banking can skew the results. Think about that accelerometer. You plug it in there, the car's sitting on pit lane, everything is flat, and you're going to take off and head out on the track, and there's banked corners, and there's hugely banked corners, there's downhills, uphills. Some of that can skew the results, and we're going to talk a lot about that today. And I already mentioned the mounting can produce noisy data, and we're going to see some of that here in some of our slides that we're going to talk about, and we'll have a better idea of what's coming after that. So the next slide I'd like to talk about is the sensor setup. It's pretty straightforward, especially on the dash loggers. This is a MXS V2 that I'm showing here. But all of them, you will just come in and you will click on the accelerometer tab inside of your configuration. It's going to open up a dialog box just like every other channel that you do, and you have the option at this point of, you can rename it. You can see these ones are grayed out because it's a dash logger and it's expected to be in a certain orientation. But you also then can change the sampling frequency, the unit of measure if you wish, and the display precision. So another conversation that we have a lot with people talking about sensor-based accelerometers is, what is that sample frequency? We give you a wide range of what can be, and it defaults to 50 and 50 hertz, and and some people will say 100. I'm kind of a fan of 50, and other people will say even as low as 20. Now there's a reason that each one of those might want to be used. Let's say you're really looking for that every curb, and you want to see exactly, or you want to see when you hit little cracks in the pavement and you're doing stuff on the length of the wheelbase, you want to see some things like that. I mean, stuff that you need to be pretty accurate with. You have to bump up the the sampling rate, or else you're gonna every data point's only happening in this case every 50 times per second, and if something happens in between those data points, we're going to miss part of it, right? We're probably still going to see it, and you're going to see it, but it may not catch the peak. So the downside of extra sampling frequency is, number one, file size. Not a big deal anymore. We've got huge memories on all of our loggers. But the bigger downside for you as somebody that's looking at doing your data analysis is the data will typically be very noisy. And we're going to see some of that a little bit later. So the lower you go on your sample rate, the cleaner signal you're going to have right out of the box. So I'm a fan of 50, but there's a lot of folks that'll either do 20 or 25. So again, I'm not here to tell you what to do, but telling you that, hey, you have some options. Turn it, change it to something different, and go out and try it, and just do a little bit of studying on your own, and see what works for you. So the unit of measure, typically almost everybody wants G's, and 2 decimal places is what almost everybody likes. So the other thing I'd like to talk about is a lot of the information, as I've studied and getting ready for this, is these three users here that we've had on as guests in our webinars, is Jorge Seegers, Chris Brown, and Bob Knox all came and joined us in webinars, as well as Buddy Fay. Buddy Fay was on as well. Matt's going to probably send links to all of the webinars that we did. If anybody wants to go back and watch any of these 4 webinars we did with these great guys talking about their books and how they put those together, do that. I go back and I review those. The Buddy Fay book doesn't talk a lot about GPS and comparing those things, so that's why I didn't list it here. But wonderful book, still a great book. But these 3 books, I go back and I look at them. And preparing for this one today, I went back and read up on sensors and accelerometers and different things. And I just wanted to share those with you again. Those are great books. If you want to go buy those, they're available on Amazon and bookstores and different race shops all over the place. So I enjoy all of them. I use them all a lot. Let's start talking about some examples. This is kind of interesting, and I think you'll find some of this interesting. I'm going to glance over before we jump into some of the examples and look at the questions that have come in so far. And Kyle Watkins asks, and just to have the definitions right, GPS based is a speed delta calculation. Yes, yeah, that is true. It's not necessarily speed delta calculation. There's more to it, I think, than that, but I think generally speaking, that's probably a good example of how it works. But there is a lot of other things that goes into it than just speed. There is data points that are happening every 25 samples per second. There's a lot of math that goes on, and then the rotation, the heading, all of that is creating the lateral and longitudinal G's information, plus speed, obviously, too. Doesn't the zero function in Race Studio 3 zero all the axis in the dash? Yes, it does. That is, once you get to that point and you get into you go to your live measures, and you can go to the calibration side and have the car leveled up and ready to go, and press that calibration, and all 3 will be set to zero out. Well, this good example right here on the page we're looking at, when it's going up the straightaway, it's basically 0 on the longitudinal, 0 on the lateral, and 1 on the vertical. And that gets a lot of people confused. And so a good time to talk about that. The vertical is Z, it's straight down. And you and I standing here, we have 1 G of load on us standing here. And that's why we follow the convention of -1 is the load at rest in the vertical axis. So everybody keep that in mind. Some people will go and zero that out and fight that and put an offset in there and zero that out. But I've gotten used to leaving that at the -1 to be at right height. So if your car is ever off the ground, and we're going to see some examples of that in a little bit, if this line on your vertical goes to 0, the car has no load against it. So we will see that in a little bit. So to install Solo 2 in a motorcycle, I need to do some math channel calculations to get it right. Info regarding the lean angle. It is not possible to use the roll rate directly. That is absolutely true. I'm actually going to show you some motorcycle data, and we're going to take a look at it. It's not as bad as what you might think, but if the bike leans over and now the Solo is leaned as well, there is a there is a delta. There is a difference there in what it's measuring with its sensor versus the orientation of the bike. That is true. We'll talk about ways of getting around that. Point being that doesn't need to be mounted square. I usually have it set off the side, so it's like 20 degrees from traveling square. Kyle, as long as you understand that and understand that you're 20 degrees off, do the math at some point and take those angles and take the, I think it's cosine. I've been a long time since I've done it off the top of my head. But if you take an angle, the value of your laterals, and you take that 20%, the cosine of that angle off of it, you're going to find the bigger the angle, the bigger the difference is. And it doesn't get huge until 10, 15. It starts to be noticeable about in that range. But a little bit of off and on. No reason to put a square in there and get it perfectly square, because 5 degrees either way is not huge. But once it starts to rack up, you will find a number that is getting to the point where it's giving you bogus data. So, and a great way to check that is just lay over what we've done here. Lay over your lateral G's from the sensor versus your GPS based and see how they match up. And if you're always seeing them skewed one way, you know that it's because of the way you've mounted the display. Let's talk a little bit about this first one here. We'll come back to maybe some questions a little bit later. The high bank road racing. This is Daytona. Many of you probably recognize the track. This was an interesting one because again, we're not saying that GPS is better than sensor or sensor is better than GPS. It's where does one work better than the other, and where do we find these issues if there are issues? And let's talk about that a little bit. Here is lateral G's. I've circled them in this graph, and you can see that it's named back straight here, but that really is getting on to the coming out of the infield and up on the banking starts right here. That's the acceleration down to the bus stop here in the back. So it's this entire area right here. And look at the difference between what the GPS is saying is the lateral accelerometer values versus what the lateral accelerometer itself is saying the value is. Substantially different. And the down here in NASCAR 3.4, same thing. And it doesn't really need to be said, but let's chat about it a little bit. When the car comes out of the infield and jumps up here onto the banking is very steep, and you're changing direction as you're going around that corner, and the GPS is recording that as that directional change, right? Even though the antenna is laid over a little bit and the car is actually at the 20-degree banking or whatever the numbers are there at Daytona. It's very steep, and you're going around, and the GPS is more accurate in those cases. But the lateral accelerometer sensor-based data has very little lateral G's because the car is leaned up in the banking, and what we're measuring there is because the gauge is totally already the same angle as the banking. How much force is actually going up to the outside of the track? It's not nearly as much, so it's a lower number. So then the next part of that might be fun for you to play with is number one, I would trust the GPS based ones on highly banked tracks. A little bit of banking, again, not a big deal, and we'll see that in other spots. But what I did throw up the vertical accelerometer, pretty noisy in this case, but we'll actually play with that a little bit right here towards the end of this session today. But look at this -1 is kind of going along here. The car's bumping up and down through the track, through some of the infield. And then look at how it dips down, and it's almost a 1.5 negative G, so almost an extra half a G straight down into the seat from the banking. So where this separation happens, the vertical is increasing. Same thing over here where the in turn 3.4, NASCAR 3.4, you can see that the vertical loads are increased even though the laterals are not because of the banking. just something to open your eyes and say, okay, well, yeah, that I see that there's a difference there, and again, you understand why, and then you have the opportunity to make the call of when you want to use which sensor. And but look at the rest of the track. Look how close, even though one's calculated and one's measured, the look how close they are. Look how accurate they run together. And even the longitudinal, slightly different in the banking. You can see a slight separation, but small. And so it's not as affected as much. The numbers are quite a bit smaller, obviously, with the acceleration rate at 120, 130 miles per hour in a spec MX5 Cup car here. So just an example of one thing that we see that's kind of interesting. So you go from the high banks at Daytona to our next slide, which is the absolute opposite, right? Off-road UTV in an off-road race in Minnesota. What's interesting here is typically when I go to an off-road race, I use the GPS almost exclusively. These cars are trucks, the buggies, the UTVs, all kind of fit into the same. They're doing the same thing out there, but they're bouncing, they're jumping, they're up on two wheels as they're cornering. There's large jumps where they go steep uphill. They go through the air with 0 Gs and then they come back down. And there's a lot of elevation change. There's a lot of banking in the corners, and which just messes with the red lateral sensor-based traces and the longitudinal here. So the kind of interesting. So the GPS typically is more accurate in this world. What's interesting though is that here we are. I put the vertical down here again at the bottom, and then circled these plateaus. Take a look at that. That's kind of an interesting and fun thing to look at. And the off-road racers that use AIM data loggers in their cars and trucks have become very good at using this information. This is vertical. So again, when the race truck is in the air, it's like falling through the air, right? There is no force on it. And since -1 is when it's sitting flat on the ground, when it goes up here and plateaus at 0, that's when these UTVs are in the air. And trucks, and I only circled the bigger ones, but there's a ton over here where they're in the air for shorter bits, right? And then the opposite of that is when they're in the air, we can then check, the teams are checking the drivers, making sure they're lifting off the throttle correctly. Maybe the best thing to do is shift in the air. Sometimes on the 4-wheel drives, they can if the truck or the UTV has the nose high, they can tap the brakes, and the team can see that, and then all of a sudden it'll pull the nose down because of the way that when your front tires lock up, it pulls the nose down like the guys on supercross bikes have done for years. They're doing that in off-road cars now. And and so you can see if they're doing that. You can see the next step of that is when they land, right? Look at every one of these plateaus. There's a big spike down. Naturally, that's when they're hitting the ground, right? So it goes right past the 1 G and right down as high as nearly 4 Gs on this one down here, which is, it starts at 1, so it's three additional Gs down is this spike here where the car hit pretty hard. And so the driver can, it's kind of their job not to land in holes and in things that will tear stuff up as well. So if they see that they're landing in the wrong spots or jumping the thing too hard, we can see that from the data as well. And then finally, the last thing, that these off-road vehicles, they have a ton of power, and they some of these trucks are as much as 900 and some horsepower. And when they're in the air, if they stand on the throttle and come down on the ground with all that power, it can just break drive lines, it can break ring gears and axles. And the opposite is just as true, especially on the faster tracks. If they don't get back on the throttle at just the right time, they'll actually land with no power through the drivetrain, and the tires will all of a sudden backlash all of the drivetrain going forward, and it can actually break things the other way. So it's really up to the driver to be on the throttle at the right time, not too early, not too late, and they're able to see that very clearly with these vertical accelerometers in their off-road world. So again, it's kind of funny, but same data, using it slightly different ways in different forms of motorsports. It's kind of fun and kind of cool to look at. The next one, which is one that not too many people here will do too much of, but it's another interesting way of looking at data is drag racing. The We have another, here's a time when absolutely the GPS based longitudinal Gs will not work for what we're after. In this case, the red one is the sensor based, and I can see exactly when the driver let go of the line lock and left the lights because of the big spike in the sensor based uh, accelerometer. But look at how the GPS longitudinal base kind of just rolls up when you're at a dead stop and then start. It takes a little while for everything to get moving and get the math done there, right? So in this particular case, standing starts are not great for the longitudinal Gs. So in this case, we use 100%. We use the longitudinal G sensor based information. I also then included in here the lateral and the vertical. We do not have a vertical from the GPS, obviously, so there's no blue line here, but you can see the noise of a pretty stiffly sprung drag truck, even though it's a smooth track, but there's a lot of harmonics and there's a lot of noise in that in these sensors. No filtering here at all in this particular case, but just to give you an idea of how it all kind of lines up. Once you get up to speed, the GPS based stuff works pretty good, but from the standing start, not so great. The next one is another a little bit of an odd usage, but now we're getting closer to a lot of people here are road racers and do some things. So let's look at some road racing data and get take a look at it. Maybe a little bit of a different thing to look at. We're going to look at the vertical again a little bit more. People don't use it as much, so I wanted to use a few slides just to give you some ideas to kind of look at. And not everybody has shock sensors. So this is some of Matt Romanowski's data that he loans us and lets us have. And but you can see here, speed up here in the top. There's a corner here that the track direction is coming down our imagery here. You see the blue dot right there where the cursor's at. It's just about to hit the curb right there, right? And so we can see the vertical is buzzing along just fine, and then all of a sudden it takes a hit, right? Boom. And remember how the off-road car lands and there's a big shot down. Well, the curb came up and met the car, and then the car rebounded up, and then there's a little bit of a rocking and rolling there a little bit, and then the car settled down and went. The fun part to look at just as much as that is the shock sensors and the lateral Gs based on that. Let's say you don't have shock sensors. Well, you certainly see this and you kind of know what happened here, right? If you had shock sensors, but you're not looking at the vertical, you probably have a pretty good idea of what happened here. So it's interesting to know that you may not have sensor X, but there's almost always a way to work around and get some of this information in different ways. Here's the two front shocks, and he's just buzzing along, and all of a sudden up is the wheel coming up. The way that these are configured on the car is when those lines come up, the tire is coming up. That's the way I tried to remember it. So look at both front tires went up, both rear tires went up. So it didn't just catch the curb on one side. I do not know that curb, but it appears that he caught the curb with both sides of his tires, right? Both right sides and left sides. That's from the shock data. It certainly looks that way. And then you can see it go up, and then you can see all four tires. First they went into compression, and then they came down in rebound, and they came down farther than they were before. So the car was nearly off the ground, right? If you look at the placement here, it got up to about a half a G. So if it got all the way up to 0, the car would be totally floating through the air, and like the off-road trucks. But got up to a half, and then it hit the ground again and came back up, and then on down the corner, and then finally the last thing I would look at here is look what happened to the lateral Gs. If you don't look at your verticals and you don't have these, and you see a release of lateral Gs like this all of a sudden, with the additional information here, it's very clear what happened. Once he got that curb and the car just releases and probably moved over probably 3 or 4 feet in that 100 feet or so that he was traveling through there at 87 miles per hour. But the release of the lateral G shows that the tires lost lateral grip as well. Kind of interesting. The Matt says, "I wonder if that has anything to do with the spindle I was welding back together today." Yeah, good chance, right? Good chance. The your Porsche is not an off-road UTV. The the so kind of interesting. We look at a little bit of verticals there. The the next slide is kind of interesting. We're going to move right into some additional information. This one we're not going to analyze a bunch of this data, but and it's pretty busy. But I thought it would be fun to take a look at it. This is motorcycle data, road race motorcycles, and what we're looking at here is the speed trace on the top. A habit of mine, speed trace is always green and it's always in the top box, so it lets me know where I'm at on the track personally. I also like to rename my track segments to give me an idea, and then I also change the colors in the background to faintly match the segments. You'll notice that on a lot of my traces. So the kind of something that makes it easier for me on my eyes and understanding exactly where I'm at when I'm looking way down here. So something you might want to consider. What we've got here is a series of corners. Right here is where the blue dot is. It's hard to see in the map when it's through the projection, I'm sure. But so he's on the brakes. We've got the front and rear suspension. Look how, in this case on bikes, they typically when you hit the front brake and the graph is going up, it's because the forks are being compressed. When the bike is wheeling, the value will be a zero value. It'll go all the way down to full droop. Full droop is zero. So where you see all of these lines here, right at the bottom, is that one's barely, the front wheel is still on the ground, but very light. Here it was a full wheelie, and there's a couple others where the tire was at full droop, right? So when you see this jump way up, it's because they're on the brakes and the front forks have collapsed. Not all the way, that you can see where this one here was really close on that braking zone, and that probably is right on the edge of bottoming out. And when it bottoms out and they're hard on the front brakes, I'm told, I'm not a motorcycle racer, but I'm told that can get a little hairy. So that's why they all have suspension pots, is they really watch the braking area in that front fork and understand how hard they can brake and when that gets close to bottoming out. And spring rate goes to infinity, and not a good thing, right? I know we have somebody on here that is very, very good with this motorcycle suspension here with us today. The same thing with the rear. So this one pumped all the way up, the rear went all the way down. So the rear is almost at full extension. So the bike is stood up on its nose. And then what we also added here was pitch, roll, and yaw. The 3 sensors we haven't looked at yet. And it's just kind of interesting to watch as the bike comes down and then goes through this series of corners here. And you can see the pitch. Number one, that is the bike, the nose going down and the nose coming up is it's the pitch, just like on an airplane, pitching. We can see when the rider is turning into the corner, and there's a series of corners there where you're bringing the bike up and over to the next one, and then the bike does pitch quite a bit through there. And then the roll rate is the degrees per second. And by the way, all of the gyro stuff is not the degrees that it's laid over. It's not saying it's 30 degrees in roll. It is how fast you're rolling it. It's the roll rate. It's degrees per second. So that's what you're looking for there. That lean angle is something else that many bikes have in their ECUs nowadays, or we can calculate it as well. A little outside of the scope of this one, but go back and watch any of Chloe's videos, webinars she's done with us, that Chloe Laren, and she has talked about lean angle and ways of calculating it or looking at it from the ECU. So you can see the rider is rolled the bike back and forth through this series of left, rights. Here, you can see that here. And then the yaw rate is the bike, even though it's laned over, the bike is changing direction. That's the yaw, right? We think of yaw as a car and drifting kind of a thing, but it really is just as much change of direction. That's all yaw really is as well. And you can see how quickly the rider is changing direction. There's some corners he changes direction very quickly. Other ones that are larger radius corners, I'm sure, or there's a lot slower of that yaw change. So lots of information there from a bike, a car, everything you have, we have the same information. So interesting stuff on the road race bike. The next one we're going to look at is oval dirt kart. Here we're going to throw in a little bit of an analysis tip that I tend to follow quite a bit in my analysis work. But the first thing is, this is a Micron 5. It's on a cart, a dirt cart. Now again, everything is solid mounted. The engine, the Micron, everything is mounted solid. And I colorized the accelerometer Y, is what we call them in the Micron. Look at the noise, look at the vibration, the harmonics in this cart. Now we are much shorter period of time here, right? This is 4 seconds from here to here, right? This is at 4 seconds since the lap. Laps are probably 9-10 seconds, right? So the very short laps, but a lot of variation in the accelerometer data. Again, there's reasons for that. Number one, I just mentioned the engines are single cylinders and they're just going like crazy. No balance shafts, nothing like that, and they're mounted solid. And then the Microns are everything from front to back. There is no suspension to take up anything, so you get a lot of harmonics into the accelerometers. I know this is some of David Smith's data from Kart Speed, I'm sorry, and he's used this data in some of our webinars in the past, and I know he's thinking of and maybe has already adjusted how he's mounted some of his Microns in there. But what I've done here is a couple things. Number one, the blue one is the GPS based. It's still a little noisy because that cart is moving around a lot. They very, very high speed. Almost two and a half G's in the corners on dirt, and it's rough, and it's they're moving. So even the GPS has a little bit of noise to it. But what these folks really want to know is they want to know their average G's through this corner from this point where they enter to where they exit the corner. And what they really want to do is not know a peak. And a little hard to get the peak from some of this because it's kind of peaky. But what they really want to know is how much G's did they build through that entire corner. And one of the things that I do a lot is I use the delta function, and I make my, I predetermine after the first session or two, we've got them marked as turn 2 and 3. It's 1 and 2, the straightaways. We could rename these, but this red and blue is the cornering part. It's after the driver has turned in. The build has already been happening in G's about at 1 G to the end of 1 G. So everything above 1 G approximately. And then we use the delta function and we turn on the average for everything in between the cursor. And you can see here that I started at 1 G, ended at 1 G, and you can see the 3 values of the 3 different accelerometers. I haven't even talked about the red one yet, which is a rolling average math channel that we built. I'll talk more about that a little bit later. That is the accelerometer data, the gray accelerometer data with a rolling average filter applied to it is the red one. And but we can see that the average G's through that corner was 1.72, 1.69, 1.56, only about 1/10 of a G off on all of that noise and mess of that entire corner. And that really is what they want. They want to know they changed their tires, they changed their setup, they changed their driving line, the track changed, and they really want to know how good the cart is cornering in this end of the track and that end of the track. And they do chemicals on their tires, and they do all sorts of stuff. And this has been a very, very helpful way of doing the math instead of just looking at the peak or, kind of eyeballing what it is, but actually do a value of finding what the average of the entire corner is. And that's what those numbers are there for you. We'll talk more about that rolling average here in just a moment. The next one we want to talk about is sprint kart racing. Again, Micron 5. And the same problem as what David's dirt kart has here a little bit. and the Sprint Kart has is they mount their data logger, their Micron 5 display is on their steering wheel. So here's another time that this is an issue for them that they just need to understand and work with is when they turn the corner. And this is why you see a steering position sensor in this one. We're going to take a look at a corner here. When they turn the corner, they turn their steering wheel 1.3 degrees there, but as much as 20 degrees right here at this corner. 20 degrees of steering angles. They've just changed that lateral G's, kind of like the banking at Daytona, right? So they need to be a little bit careful and understand which is the right sensor for them to use if they do that. And what I thought was interesting here is to look at the values that how big the change was. I had really never studied it as deeply as I've done in the last couple of days. So here we are, we're steering this Micron. Accelerometers are being tipped up with the steering wheel angle. Let's just pick this spot here and kind of come down. Look at the difference between the lateral G's, GPS based, and the accelerometer Y, which is the sensor based lateral G's. You can see that there is some almost on top of each other here at smaller steering wheel angles, and there is some separation, but not as much as you'd think. Interesting, right? So if you sprint kart race and you got a Micron and it's bolted to your steering wheel, start to understand that maybe this is not as bad as we all thought. Do your own testing and figure it out. You might want to use some sensor-based stuff. What did surprise me, though, was the longitudinal actually has some difference to it. And what you need to understand is these steering wheels on these karts, they're not only just the mounting there and it's just not straight and they turn it, but they're tipped. They're like a 30-degree angle. So when they're turning it, it's not only affecting the lateral, but also the longitudinal. And it seems to have a little bit more effect on the longitudinal G's than it does on the lateral G's. And that's not something that I had thought through or tested enough to understand fully. And but it is kind of interesting, and I'm going to look into that a little bit more. So in sprint kart racing, it's almost universal. They use GPS based lateral and longitudinal G's almost across the board because of that the noise that's in there, and then also the Micron being rotated with the steering wheel. Kind of interesting to see. The last thing I wanted to talk about today, and was the subject of filtering. We often get, depending on how you mount it, and AIM has done a good job of doing some pre-filtering and changing some stuff so the sensor-based data used to be all pretty noisy, and it's getting better and better just by stuff that they're doing before you even see it. But here's a pretty dirty, noisy vertical accelerometer trace from that Daytona data. And it's pretty noisy. And I just wanted to talk a little bit about what you can do to help that. What is available for you if you choose to do it? What kind of filtering? There is filters that are available. If you right-click on the channel, you have a 0 for no filtering, up to a 3 is the heaviest filtering, but the filtering doesn't work great on accelerometer data. It just kind of pushes down the high spots and it rolls over the low spots, and you end up with a bit of a wavy trace instead of something that's kind of a line cutting through it, right? That is more representative. So I wanted to talk a little bit about filtering and what's available to you in a math channel. My favorite math channel that I have found that works best for me on noisy channels like accelerometers, maybe RPM that is a little bit of noisy, that we get sometimes in all different forms of motorsports, is the rolling average math channel. And I just threw it up here. This is what we're looking at here. This is that I've changed the color a little bit I went from a bright red to a little bit of a lighter red in the background of the raw vertical accelerometer data. And then I've created this math channel, the vertical accelerometer, and we've done a rolling average at a level of 9, just so you just get an idea. And I've made that in black. And then I've clicked on the, pardon me, I've clicked on the channel tag, and that bolds it. A little trick that I do quite a bit in my own mind. It makes it easier for me to see, as if I click on that, I get the min and max, but I also then bold the channel. So that's what you're seeing here. That black is a rolling average applied to that very accelerometer data. Much more useful but yet not over filtered. We can overdo things sometimes. And I suggest that if you choose to use different filters, when you're in the math channel function, just go in there and build. I tend to build my math channels when I do filtering. I'll build one and right away before I even go view it. I'll do a copy of it, duplicate it in the math channel function, and just change the different levels and maybe make 4 different levels of filtering, and then bring them all in, throw them into analysis, and then look at them and just sit back and eyeball them and say, boy, if it took away all of this noise where the driver was going through the bus stop where I know they're on the rumble strips and it should be noisy, should have some noise there because the car was shaken. If this was just a straight line through there, I've over filtered it, right? So keep that in mind and get it down to a level that works for you and is correct. The next slide, I just zoomed in on this segment here, and just to give you an idea, it's the same exact data we were just looking at, but just zoomed in where you can actually see the individual noisy line work, and then what the dark black line is doing going through it. I find this rolling average is something that works really well for me. And then the last thing I just want to reiterate this one again. I went to this this area coming out of the infield and getting up on the banking, and looked at the vertical, and along with the rolling average of a level of 9 in this case, and that's how I just named it. M. I always start all my math channels with an M, just makes it easier for me to understand it's a math channel. And then whatever the name of it is, RA for rolling average, and then I follow it with the level until I figure out the level I want, and then I'll go back in and get rid of the ones I didn't want and get rid of the 9 off of that one, and then just keep it the vertical accelerometer RA for rolling average. And what's interesting here is I wanted to see for this entire area on this vertical, I again went for this entire section here of 30 seconds worth of data, and what is the average vertical load that was in that corner, right? So I delta function, boom, boom, and set it up where we can read the average of the how far that was down from the -1 that was the standard of if the car was just sitting flat, and it was 1.2 over this entire run. Of course, it peaked in the middle. Not something I would normally measure for good information, but I wanted to show you 2 things. Easy enough to check what the average was for that area. And then the second thing I really wanted to show you is, let's say you choose not to filter and you choose to get an entire corner of lateral G's, let's say, or an entire braking zone, and you use the delta function and go across. Look at the values. -1.2 is the average from here to here of the rolling average one, and it's also the same as the raw data that came out of it. So even though all these spikes are here, and we have one that looks a little nicer and one that's all spiky, noisy, when you do it over time, over a little bit of time, the averaging of that ends up working out. So if you don't choose to do the math channel, try some of the stuff on your own and feel more comfortable doing it. But if I was looking at a long corner of the carousel at Road American, I wanted to know what the average cornering forces are once they all exceed 1.0 lateral G's. It's like 13 or 14 seconds of being at that high. And all I do is I just pop with the delta, and I have an average lateral G's that every car did, right? And you can get a pretty good handle on how the different drivers are attacking things, or your different teammates, or if you've got a shock that's you just changed some settings, or you went to new tires, or all the different reasons you might want to compare lateral G's. Doing it on an average like this is very, very helpful. So that I think is going to finish up the examples. I haven't had a chance to keep up with the chat, and I don't see anything that's in the question and answer, so I appreciate that. So we're going to kind of close this one down here a little bit, but I hope that gives you some ideas. The main thing I was going for here today was discuss the difference between the two, obviously, and then give you some examples of not just that GPS based accelerometers are the best, and you should always use those, but there are times when you should use one or the other, and give you some ideas of ways to test and ways to look and ways to filter to get those to the way that it'll work for you. So hopefully hopefully that has done some good for you guys. Later this evening, I will be downloading this video and getting it up onto YouTube. We have a whole bunch of videos there. It's growing all the time. There is a function that Brick from our Roanoke office has been building more short form videos, very specific functions on different things. We have a playlist of nothing but that now, and you can go to the YouTube site here, the YouTube at /aim data. If you haven't been there, go there and go to the playlist button, and you will see. I think he's up to 7 or 8 that he's got done, I think, already. So there's a bunch of videos there that you may or may not have seen. Make sure you go check those out. They're current, they're up to date, and he's adding like one a week at this point. So go visit our YouTube site. Make sure you subscribe and let us know what you think. Customer support, boy, Matt just throwing the link up there for you. The link will also be in the description for those of you that are watching this one, if you want a quick link directly to the playlist later. The customer support, we're out there doing what we do. We want to make sure that you get the most out of your AIM hardware and your software. So give us a buzz if you don't see us at the track. 800 number there. Give us a holler. Let us help you get the most out of your stuff. Our next webinar is going to be another one like this, kind of the fundamentals of data analysis. But next time we're going to talk about pressure sensors and temp sensors. We're going to talk about some of the different things of those and maybe some good best practices as far as configuring, calibrating, and using those in a bunch of different examples as well. So it will be a good time. The contact information, if you have any questions of some of the stuff we've talked about tonight, or if there's anything that you might want to, need some information on anything, there's my email address, roger@aimsports.com. Happy to chat with you. The email is always the best way to get a hold of me. Pretty busy, and sometimes the phones get a little crazy. So if email me, I am always able to feed in, and I work a lot of hours, and email works for me sometimes. So drop me a buzz if you want to have any questions. And as I started off, before we actually started recording for this one, I mentioned that I was looking for webinar topics. If there's some topics that those of you that are watching this either now or later, please drop me an idea. You don't have to put a lot of meat on the bones on the topic. I probably understand what you're after, but give me the highlights of a webinar you'd like to see, something we may not have covered or we've covered in the past, and it's time to redo it, right? Get a fresh look at it. Let me know. We're filling out our late 2024 calendar and starting to make plans for our 2025, early 2025. So make sure you let me know. I would appreciate that. So thanks everybody for coming again. A wonderful time as always. I hope you enjoyed it, and look forward to seeing you at our next one at the end of the month. Talk to you guys soon, and have a great night.